Sweet, thanks.
Okay, I think we can get started now. This is the second part of the spoken digit recognition project, and in this part, we'll be figuring out how to load the audio files that we have, as well as like visualize them and like put them into a data set class we can load and put into a model. No, you did not have to. Part one was just how to use GitHub. This is separate. So these are the 5 sections that we will be going over today. They're pretty quick, and these are just like the basic sets of information you need to know to be able to get through this. So first we'll talk about neural networks, because that's sort of like the core of what we're doing here. And essentially, a neural network, in a simplified way, kind of looks like that. It's basically just a really complex input-output machine. You give it some piece of data and it will give you some output, which is usually whatever you trained the network to give you. And the way it works is that each layer is like a set of numbers or a vector, and you can multiply it by another matrix of weights to get the next layer, and you do that to the next layer until you go through all of them and you end up at the output. It is a lot of math, and mostly it's linear algebra and multivariable calculus, but to actually do it here in this project, you don't really need to know exactly how it works, but that's sort of like a very quick summary of how these networks work and what they do. If you want to learn more, you should research that yourself. It's quite interesting. And then to get more specific with the neural networks, we're going to be using a convolutional neural network. And the way this works is essentially you give it 2D like data. Usually it would be an image, but in our case, it'll be an audio file that we sort of convert to sort of similar, like look kind of like an image. And what it does is it goes through like this like same size chunks of the 2D array and like scans through. And then for each chunk that it looks at, it performs like a mathematical operation on it, and it kind of like summarizes just that chunk. And the effect of this is that you kind of get like a broader picture of what's actually in this data you're looking at. It kind of like cleans up the noise and like extracts out the most important parts of it. And this is kind of the most important part of how we're going to be assembling this in the next step, or in the next workshop. And to do all of that, we are going to be using PyTorch. Like I said, all of those things, especially the convolutional neural networks, they require a lot of math. And so to kind of hide away that math and make it more accessible to anyone, we use something called PyTorch. There's also, of course, competing libraries like TensorFlow, which do the same thing. Essentially, you can write a couple lines of code and you can make those layers, as you saw in a couple slides ago, without having to know the math and without knowing fully how it works, just like how to use it essentially. And to get more specific, PyTorch like offers specific classes and objects for like individual layers you can combine into like big models, where the models will like automatically do the math for you as long as you give it like properly structured data. So the part we're doing today using PyTorch will be the data set and the data loader. The data set is something you construct yourself, and essentially what it does is that it knows where to get data from and what to do with it, and then it outputs that processed data in a format that PyTorch can read and put into a model to like give you an output. And data loader takes in a data set and essentially gives you batches of data, because when you train a neural network, you have to give it like small chunks of the data you're using. It can also augment the data, which we'll talk about later. Okay, so we're working with sound for this project. And so this is kind of just like a brief overview of physics class, I guess, what sound is like. it's usually represented as waves, and we can actually visualize this later today, where the height of a wave would be the amplitude or how loud the sound is, and the spacing between like each wave would be the pitch or how high or how low the pitch actually is. And when you load these into Python, they are essentially given in the form of like a one-dimensional array or a list of numbers. And this list of numbers will represent sort of like the loudness at that specific moment in time. And the final concept to understand is sampling rate. So obviously in the physical world, these waves are well, they're like continuous. They're not like broken up into like discrete sections. It's just like a smooth wave. For a computer which stores things in binary format, you can't like store a wave like that. Instead, you have to break up a wave into like little segments of time, and that sampling rate is how small those segments are. So in general, sampling rates are like 22,000 or 44,000, meaning that you like capture the loudness of whatever sounds are being picked up by the microphone like 22,000 times a second or 44,000 times a second. For this project, we'll be dealing with files that are recorded like 8,000 times a second, which makes them much smaller and easier to deal with. Yeah, the picture might look scary, but like it's fine. It'll be understandable. But that is essentially a spectrogram. And the point of it is to essentially take a sound wave and decompose it into the like various frequencies it's made of. Because obviously, like if you're just out in the real world, you're not hearing like one pitch or frequency or loudness at the exact same time. You're hearing multiple at the same time. And in like a regular waveform, that's not really easy to see or like imagine or picture or like deal with. But with a spectrogram, we can actually take a waveform and break it down by frequency and then see exactly which frequencies are playing at a moment in time, as well as how loud each individual frequency is. This gives us a much clearer image of what sounds are being played at one time, which makes it, of course, easier to analyze and put into a machine learning model. And one thing I'm also going to point out is that sound is, to humans at least, a logarithmic thing. So like if you have a sound of like 440 hertz, which would be, I believe, A4 on the piano, like the middle A key on a piano. If you go a note below it, it'll be 220 hertz. But then the A above it isn't 220 hertz more, it's actually twice as much because like when you increase the frequency at a low amount, it's easier for us to hear it. But when you get to higher frequencies and the pitch changes slightly, that's not so easy to hear. So actually it's doubled. So what a MEL spectrogram does is that it kind of adjusts for that and then makes the frequencies more mapped to what humans hear. And because these recordings will be human voices, we'll be using a MEL spectrogram to visualize them. And that should be all of the core concepts, possibly a little fast. So if anyone has questions, now would be a good time if I need to like go over anything again. I'm gonna assume that means everyone understood everything. So that means we can move on to the coding part, actually. There it is. So if anyone actually wants to follow along, give you a minute to like, open up wherever you're working in, and you can probably just type out that code unless you haven't installed those libraries, in which case you should do that first. And to install any of them, you would just do like pip install in a terminal and then the name. Oh, and at least in this room, can I know who is following along so I know like how to wait or anything like that? Like if anyone, can I know in this room who's following along just so I know how long to wait for things? Okay. Then let me know when like you've done installing those libraries. if you have Python already installed, then yeah, you can go to the terminal and just type in like pip install like librosa or numpy or whatever you need. Yeah. Oh, and on Zoom, because I know some people just joined. We haven't started coding yet, so if you also want to follow along and you're on Zoom, you can do the same thing and just install those libraries. And then let me know when you're done with that. Oh, so just a side note, I will upload this code later onto GitHub for anyone to see. So don't worry about not keeping up or anything like that. Yeah, I will. Yeah, if you look at the screen I'm sharing, all of the ones that have like are next to the import statements, those are the ones you need. So it'd be matplotlib, it'd be torch, and you don't have to like, yeah, it would just be torch, librosa, and numpy.
Rudra, I think we might only be able to see your Chrome tab if people are having the same. If you could just thumbs up.
Oh, I didn't realize that you can only, my bad, I forgot to switch which screen I'm sharing.
No, you're good. I do it all the time.
Can you see it now?
Yeah, you're good. Thanks.
Oh, and if you're on Zoom and you're having trouble installing any of the listed packages, one thing you could do is go to Google Colab and make a new notebook, and everything's already installed for you there, and you can just type in these exact same statements and it'll work just fine there too. So at least in this room, are we ready to move on? Okay. So first I'll explain what these libraries do. librosa is basically a library that lets you open up audio files and then it converts them into a format that Python can read, usually a array or a list or something similar to that. And in addition to that, it's also the library that lets us convert these waveforms into spectrograms or MEL spectrograms or whatever we need, among other types of augmentations. Like it can make a piece of audio longer or shorter or anything like that. NumPy is basically just like the default library in Python for dealing with matrices and arrays and that kind of thing. We'll use it a little bit, but not too much. Torch is PyTorch, which is the library I mentioned earlier that helps us like load data and have these data sets as well as eventually build the actual networks. And this part, matplotlib, is just for fun so we can see what the audio looks like visually, which I think might help it be easier to understand. I'll also have to download the data for this, and I can also show you where to get the data from. So the data actually comes from Kaggle, of course. And it's spoken digit recognition. And it will be this one, the free spoken digit data set. Six speakers, yeah. So I already have this downloaded, so I'm not going to download it again. But well, actually, I'll just you have to sign in to do it. It's not that hard to do. And then once you have it, you should move it to the. I'm going to cancel this actually. Move it to the same folder where you're keeping your Python notebook. And if you're doing this in Google Colab, you have to download this anywhere and then upload it into Google Colab. And if you're in Google Colab in one upload, there's a sidebar on the left side with the file icon. If you click on that, you'll be able to upload the data you're trying to use. Yeah, you do. It'll be a CSV file that tells you essentially what the actually like the path to the audio file, and then also what digit was spoken there. But the main thing is that it has a folder with the actual audio files in them. It doesn't have to be. Since I have this downloaded, I'm just going to move the audio files I've downloaded into the same folder as this. What do you mean by that? Okay, let me check if that is the right link then. And then perhaps this wasn't quite it. Hmm. Then let me check a different link. Oh yeah, that was in fact the wrong link. Okay. So we will link next. Okay, this is the right link. This one will have the CSV and the recordings and nothing else. Sorry about that. And I'll put the link in the Zoom. Did the new link work for everyone? Okay. So I'll move on to opening up an audio file and like displaying it. So once you've imported all these libraries, you have the recordings and the CSV next to it. The CSV, I don't think you actually, no, you do need it. But we'll look at these recordings first. So what you can do is librosa.load, and then you can point it to wherever your file is stored. So I have it. I have the notebook outside of the folder with those, so that's why I had to do that. And then you can just type in the name of whichever specific file you're looking for. We can just, I'll just pick any one of these. And so when you run that, you'll have this object. In my case, it's called audio. And what it is it's this array, and it's also the sampling rate. By default, Librosa will just give you a sampling rate of 22,000. But since we know that these files are of a sampling rate of 8,000, we can just say that here. And then we'll have 8,000. And then if we actually want to look at the file itself, we can say that the waveform is, this is a tuple of an array and also the sampling rate. So we want to look at the array. And so this is an array, and then because we imported matplotlib, we can actually look at it and see what it looks like. And so that's what the audio waveform of someone saying the digit 1 happens to look like. And of course, you could do this for any of the other ones and see if it looks any different. Yeah. So now that we've seen the waveform, which is the first part of audio that I mentioned, we can now look at what a spectrogram looks like. Lib also can do that too. So we can say, this, and that part of the library is what will produce a mouse spectrogram, which is the spectrogram but scaled for human hearing. So it takes in Y, which is the actual waveform, and then it also takes in a sampling rate, which we already know is 8,000. And you can actually visualize the mouse spectrogram as well. So I think you should do. Let's save. Sure. It'll look like this, where from 0 to 128, I believe, is like the segments of the frequencies. Whereas 0 to 10 on this axis is time. And the units are not seconds or milliseconds. They're actually, it depends on the exact sampling rate. So if your sampling rate is higher, you'll have much more data on the time axis. In this case, it's 8,000, so it's fairly short. And another thing you'll notice is that you can't really see very much. And that's because these are actually raw amplitudes. And so if you want to see more, Librosa can also convert this to like the decibel scale, which is which will show you a lot more by applying like logarithmic functions on it. And so in order to convert it into a format that's much more easily visible compared to this, you would do Libro set power to dB meaning decibels, and then you would give it the original null spectrogram. And then you would also have to type in this part, the ref equals np dot max, and that's sort of just giving it like an upper bound on like how high an amplitude can be. And I guess it's kind of an arbitrary number. And so we just give it the biggest number possible. And then suddenly you can see much more of the audio file. And it's this sort of thing that we'll be giving into a model. And so that's why earlier I mentioned the convolutional neural network, because those are used for handling images. And so what we're doing here is essentially converting audio into 2D images that we can process like square by square by square. Did you guys here get that to work? Oh, sorry. Did you get it? Yeah. Okay, because of time, I am going to move on, but if you haven't been able to get everything so far, I again will upload all of this code and the link to the proper data set after this is over. So now that we've been able to look at our audio and kind of understand what it looks like, the next part will be to actually build the data set class that we can give to PyTorch. So to do that, you create a new class. In this case, I'll just call it audio data set. And then because we're inheriting from PyTorch's dataset class, we would do that. And so what this class needs is a constructor. It also needs a method to actually get the item that you're trying to load from the data set. And the get item method will take in an index to know which item you're asking for. And finally, there will just be a method that gives you the length of the data set, so you know how many actual audio files there are. And so the first thing we'll take care of is the constructor. And so the way we'll do this is give it essentially this CSV file, which contains the names of all the files as well as what digits they represent. And that's what we use to know which audio file to load and then what label it actually represents. So to actually make that work in the constructor, we need to add in like the CSV file that actually contains those pointers. Actually, there is something I forgot. We also have to import pandas because we're dealing with CSV files. So you can just make a new cell anywhere and import pandas. And if you're in Google Colab, that should immediately work because it's there by default. So our file names and labels will be so this line will give us basically kind of a table that maps an index to a name of a file to a label, which we'd need. This would make more sense if you actually open up the CSV file, but again, for time, I would just tell you that the file names are just stored in a key that looks like that's called just file name. And if you want the labels, you need the other column in the data that's called label. And actually, I guess to make that more clear, we can try to look at this. And if you'll see, the first column is called file name, and it represents this part. There's a part that's called speaker, which just tells you the name of the person who said that digit in that recording, but it's not super important. And then we have the label, which tells you like what number was spoken in that file. So that's essentially all we need in order to know how to access a given audio file. So now if we want to get items, we know that the file name will be something that will look like this. In my case, because of where I have the recordings folder, it'll be recordings. And then you have to replace the end of that file name with whatever you're looking at here. So to do that, you have to get it from this column. And so you could do, I'll do F here. And so we're basically making a string that says like recordings slash, and it's access. Now this part would be accessing the column with all the names of the files, and then accessing the specific one that we want, which would be index. The label will be done in a very similar way, except you're not accessing the file, you're just accessing the labels like that. And so we can use what we had before with librosa to essentially, now that we have the file name, we can load the file like we did before. And instead of this, of course, we use the file name. And then we also have to convert it to a spectrogram. So we'll just say like now equals spectrogram. And then we'll take, and remember from before that audio actually returns a tuple with both the actual audio waveform as an array as well as the sample rate. So we would just take the first part. And we would give it the sample rate equals 8,000. And also there has to be a line in front of here. So that would be sufficient to load the audio and give it to you. So we can just return the null spectrogram and not the audio, the label associated with it. And if we wanted to do this function, we would just get the length of the files, or you could do length of the labels, because there will be as many files. There are labels, and the pandas column conveniently can give you the length of itself. So that should compile, and then you can essentially do this, where you say you construct the class, and remember how the constructor for it takes in the name of the CSV file. So you have to give it train.csv. That would create your data set, and then you could do dataset.getItem and give it any number you'd like, and it'll give you the label for that as well as all of the audio. And again, if you wanted to look at it, then you could just do I forgot. Okay, there might be something I forgot. So we're not going to do that right now. So that would be the data set part. And then the next part would just be a data loader, which is simple to create. It's just you use the data loader class that they give you from PyTorch, and then you just give it the data set you're using as well as a batch size. In this case, we can just pick 5. And the data loader we can't actually use right now because we don't have a model to give it to, but basically what it would do is just give you a set of 5 into the model or whatever your batch size is. And then that's essentially how you connect your data set to your model, which will be the next part of this workshop series. So that should be all for today. I can answer any questions if needed. This data loader, this is pretty much used for the next step. Well, I'll probably go over this more next time because it's more related to actually connecting the data set we made here with the model. Yeah. And I'll, of course, upload this code and I'll clean it up a little bit so that it's easier to read and add comments so that you can understand it yourself. I'll just go. So if you're on Zoom, that's all I have for you today. So you're good to go.